بسم الله الرحمن الرحيم والصلاة والسلام على نبينا محمد وعلى آله وصحبه أجمعين. Today we're going to start a new lecture, lecture 3, and we will talk about a very important topic in data science, which is called the data entropy, and this is part of chapter 3 on statistical learning. So what is the information in statistical learning? So we have already talked about statistical learning, and the information in statistical learning, it quantifies the insights or the knowledge that we can get from our data. And basically, this knowledge helps to understand the patterns in predictive models. And this is why it's important to learn about entropy and information in statistical learning and in data science in general. And basically, the equation that represents the entropy is denoted by Hx equal to minus the sum of the probability of an event, a random event x, multiplied by the logarithmic at the base 2 of the same probability. So we're going to understand why these equations represent the information that we can gain from the data. That's really important. It's related to the probability and also to the quantity of information that is carried out. And basically there is a relationship between the probability or the randomness and the information that we can get from that randomness. So the entropy, and this is the topic of today's lecture, is to measure the system uncertainty or randomness. And this particularly mapped to the quantity of information that we can get. And the key concept that you are going to learn, so this is just the outline of today's lecture, is that our higher entropy indicates more unpredictability. It means our data is mostly completely random. We cannot have clear insights of the data, okay, equating to greater information content. And this is pretty much used in predictive modeling, as the entropy helps in understanding and optimizing model by measuring the amount of uncertainty or information a model can handle or that we can reduce. So that's basically a slide that summarizes the things that you are going to learn in this lecture. And let me give you an information or an overview about the information theory. So basically, information theory is just a mathematical framework for quantifying information, communication, and uncertainty. It was first introduced in the area of communication theory, and it is fundamental to different types of operation in communication, including data compression, error detection and correction, and cryptography within data science. So we have already introduced the main equation that represents the entropy, okay, where P is the probability of an event. And historically, the information theory was first introduced, and the entropy was first introduced by Claude Shannon. This is a famous scientist. He's known as the father of information theory. Okay, if you talk about entropy, your mind goes directly to Claude Shannon, who is the father of information theory, introduced the concept of entropy in his landmark paper on 1948, a mathematical theory of communication, and that was the introduction of the entropy. Okay, because in communication you are going to transfer data, and we want to measure the amount of information that is carried about the data. So later on it was used in cryptography. Okay, cryptography need to make the data completely random, not to be disclosed. Error correction, if there is any deviation of the information from the initial data, so it can be detected also in data compression. And the Shannon work led to the foundation of modern digital communication and data encoding, which emphasized the importance of entropy in measuring information efficiency and transmission capacity. So in our context, we are going to learn the entropy in the context of data science, okay, where information theory principles guide data encoding, compression, and transmission processes. So the entropy is used in machine learning, basically for feature selection, okay? And how this relates to the feature selection, we're going to try to find out what are the features that would have an impact on the prediction of the data. So the entropy, it can measure the amount of information that the features can carry out that will impact on the data. Okay, and let me give you an example. For example, if we take, for example, the name of an owner of a house, maybe this name will be the same for different type of houses with different prices. So it doesn't carry any information. So the entropy here is 0. It means that the name of the owner of a house is not a feature because it doesn't carry any information that will impact the predictive model. So when the entropy is 0, this should not be selected as a feature. But when the entropy is high, it means that the change of this feature will impact, okay, the output of the predictive model. It means that this feature will introduce some kind of randomness, okay, that we try to put into a prediction model. It is used also in assessing the model complexity, and we are going to study this later on after we introduce the whole concept of entropy, and also in the decision making and predictive modeling. So let's take a small example to understand the relation between probability, entropy, and the information content. Okay, so we already mentioned the definition of the entropy as it quantifies the uncertainty or randomness in a system, and it is measured by this equation. Let's take a simple example of coin tossing. It can be flipped, it can be tail or head. So if we consider that this event is these two outcomes are completely independent, usually it will lead to a uniform distribution. صح ولا؟ Okay, we will have a uniform distribution. So we will have a probability of 0.5 and another probability of 0.5 either for the tail or for the face. So in this case, it's completely random. I don't have any skew in my mind that it's likely to be tail or it's likely to be face. It's completely random with a probability of 0.5 in average. So in this particular case, if we measure the entropy of having here 0.5 and 0.5, we're going to have an entropy equal to 1. It means that we need to have 1 bit to encode the information. And 1 bit can carry 0 or 1, so we have two possible outcomes. Okay, two possible outcomes here. So we have an entropy of 1. We can represent the information with 1 bit because this bit can take the value of 0 and 1. Look now, we're talking about bits. So we have binary values, either 0 or 1. And this is why the entropy is high here. So imagine that the coin is broken, and every time I toss it is going to have a tendency to flip on the tail more than on the face. So in this case, we talk about a bias distribution. Maybe I will have 0.8 to have the tail and 0.2 will be on the face. Okay, let's assume that we have a bias distribution. Now, if we calculate this information here, we replace by 0.8, 0.8, and 0.2, 0.2, we're going to have an information that is much less, around probably less than 0.5 or around 0.5. It means that the information here is smaller. Why? Because I have less uncertainty. We've mentioned that the entropy is related to the uncertainty on the information. So here I have a big uncertainty. Here I have a reduced uncertainty.
Because there are more tails.
Yes. If, for example, I'm going to say 10 times that is going to be on the tail, I will be 80% correct. I have less uncertainty. Okay? So the amount of information here is going to be smaller. It's going to be much smaller because we have reduced uncertainty. I am more confident about the outcome. When I am 100% confident, it's 0. There is no information. There is no randomness. Okay? So this is why how we need to understand the concept of entropy and how it measures the randomness of possible outcomes. So in conclusion, the entropy links the unpredictability to the information content. And they are kind of opposite. Okay? High unpredictability. Okay, no, it's not, they're opposite. They're like proportional. High unpredictability, it means high information. Okay. Low unpredictability, high predictability, it means low information. Okay, so it's inversely proportional to the predictability and proportional to the unpredictability of the outcomes. And now the question, why we use logarithmic in entropy? And that's an important question to understand. Okay, so we use the logarithmic function because usually the logarithmic, it quantifies the information content. And we use the base of 2 because it reflects the binary encoding in bits. Now in probability we have also 0 and 2. In communication, when you send bits, every bit can be 0 or 2. So look at the relation here. The equation is that we're using, it's the sum of the product of the probability multiplied by the log of that probability. And here we can observe a relation between the probability and the log of the probability. When we have a high probability, what does it mean, high probability? It means high certitude and less unpredictability. So in this case, the logarithmic of 2 of that probability is going to decrease. Okay, I have less information. P of x is high, it means I am more confident, it's less unpredictable, it means I have less information. If P tends to 0, the amount of information will be high, okay, because it will be highly unpredictable. Okay, and look now, we draw, this is a simple Python code that draws the probability in the x-axis and also the information content in the y-axis, which is calculated by minus NP of log 2. Okay, it's only log 2 here. And they are inversely proportional. Okay, it's decreasing. Okay, when the probability is high, I will have information equal to 0. And when the probability is low, the information is going to tend to infinity. Okay, and this is why we use the product. So you have, when the probability is high, the information is low, so it's going to tend more toward 0. Okay, so it's like a weighted product of the information. So I'm going to weight the information content with the probability. And we are going to have the sum of the weighted information, which will give me the whole information. Okay, so every bit, every outcome will give me a certain amount of information, and the whole entropy will be the sum of all this information. So I'm going to have like an average about everything going on that particular model. Okay, so certain event P of x equal to 1, they lead to no information as we already introduced. So the reason of using logarithmic in the entropy is because logarithmic in entropy articulate how unpredictable translate into information content. It's this relation basically. And this highlight the inverse relationship between probability and information gain. Is that clear?
Why can't we use different bits?
Because you have bits, 0 and 1. That's why. And this is now, I'm going to explain why we use the logarithmic of 2. So the entropy started in the communication context. And in communication, we use binary values, 0 and 1, okay, in digital information processing. Everything we are going to convert it into bits, okay? This is even in digital logic, okay? Everything is binary. We transfer every number to binary. And the log 2 of n, it calculates the bits needed to send n distinct messages. Okay, so for example, if you have 4 messages to send, you have 4 outcomes. In this case, you will need 2 bits. So the logarithmic of the logarithmic at base 2 of 4 will be equal to 2. And this is a simple Python. If you have 1 outcome, 2 outcomes, 4 outcomes until 256, it will calculate the number of bits. So this is why if you want to represent a 256 numbers between 0 and 256, you're going to use 8 bits. Okay, so the log 2, it encodes the amount of information that we would like to encode. This is why it's related to data encoding, okay, in digital logic and in communication context. Okay, so the uncertainty reduction quantification, the information reduces the uncertainty about the sent message. And the logarithmic of base 2 measure this reduction by representing the information as binary questions. So instead of having 256 values, we're going to have a combination in 8 bits, okay, values in the binary context. Okay, this is just the Python code. We calculate the outcome, okay, using calculate bits, and this returns for 1 bit, for 2 bits, for 4 bits until 256. We have 8 bits encoding. So let's talk about the foundation of information theory and the main concept. So mathematically, the formulation of the entropy for the discrete variables will be hx equal to the negative value of the sum of the probability of an event multiplied by the log at the base 2 of that probability. And for the continuous variable context, we're going to use just the integral instead of the sum, because here we have continuous values. And these are two examples of coin tossing and dice rolling. You know, in the coin tossing, we have two possible outcomes. Okay? So if we want to measure the entropy, which is the number of bits that we need to have, and considering that we have independent events, the head and the tail are completely independent, we're going to have 0.5 probability for both. And calculating this expression of the entropy in the discrete variable use case, okay, we're going to have 1 bit. This will lead to having 1 bit. In the case of dice rolling, how many outcomes we have? How many possible outcomes? 6. So we're going to calculate this, the sum from I equal to 1 to 6, 1 divided by 6 multiplied by the log 2 of 1 divided by 6, and here it gives the value of 2.5258 bits. So here we have higher randomness because we have uniform distribution among 6 possible outcomes instead of 2 possible outcomes. And so this is highly random, and this requires higher, okay, bit encoding, number of bits to encode the information. So the information gain here is higher because we need to encode that in 2.58 bits because we have greater randomness and unpredictability. Now we talk about the conditional entropy and mutual information. So what is the definition here? Imagine that you have two random variables, x and y, and you want to calculate the conditional entropy. It's like we calculate the conditional probability. Okay, so the mathematical expression of the conditional entropy is hx given y and will be equal to the sum of all possible values of x and y, the joint probability pxy multiplied by the log 2 of joint probability pxy divided by the probability of y. And so this is the equation for the conditional entropy of x given I know the value of y. And let's try to, okay, on the other hand, the mutual information, it's like the joint probability, which is equal to I, x, and I. So this is the information of having both the joint event, and this equal to the sum of pxy, the joint probability, multiplied by the log at the base 2, the joint probability of pxy, divided by marginal probabilities of px and the marginal probability of y. And this can be expressed as ixy equal to hx minus the conditional probability, conditional entropy of x given the y. Now let's try to understand this based on the example. Let's assume that x and y are completely independent. So this means the joint probability is equal to the product of marginal probabilities. This is known in probability, okay, the joint probability. And let's assume that px is an array of 0.5, 0.5, and the same for y, it's an array of probability 0.5 and 0.5. So if I calculate the joint probability using this formula, we're going to multiply 0.5 by 0.5, so we're going to find 0.25, 0.25, and 0.25, 0.25. This represents the joint probability over here. So now I can calculate this conditional probability, which is equal to joint probability that I have here, multiplied by the log of joint probability divided by the probability of py. So look at this picture. Now, if I calculate the entropy, because I have all of them are 0.5, it's completely random. So the entropy of y alone will be equal to 1. Already calculated. This is like the coin tossing. And then the conditional entropy of h, y given x. It's equal to 1. Why? Why it is equal to 1? It is equal to the same as hy. Because x and y are independent. Okay? So if you know X, you don't have any information about Y. They are completely independent. And this is why the joint probability is 0. Or, sorry, it's not the joint probability. The mutual information is 0. Okay? Because here, look now, this is the log of 1. This divided by this is equal to 1. So the information will be 0. They are independent. Okay? It means the knowledge of one variable doesn't give any clue about the other variable. They are completely independent. Does it make sense? Okay, so this is the mutual information. Okay, the mutual information is equal to 0 when the two variables are completely independent. Now let's consider some kind of dependency between X and Y. And here we're going to assume the joint probability equal to 0.3, 0.2, and 0.2 and 0.3. And we can calculate Py as the sum on the x-axis. Okay? That will give the marginal probability of Y. Now, calculating the marginal probability, so it will be 0.5 and 0.5. In this case, we will have the entropy of Y is equal to 1, because we have 0.5 and 0.5. Now, if we look at the conditional entropy here, okay, the conditional entropy will be slightly smaller than 1, 0.971. So what does this represent?
There's some dependency.
Because there is some dependency, so we have less uncertainty. Okay, the knowledge of X will give me a slight information about what could be Y. Very small information, but it's not completely independent. Okay, so you can see that the conditional entropy here is slightly smaller than 1 because there is a small dependencies between both of them. Okay, so we can see it's close to 1. And now the mutual information is not 0. It's something around 0.029 bits. And because we have some dependencies between both, and this value is just 1 minus this value, okay, which represent the mutual information gain. Okay, so this gives you a little bit of understanding about the relation between dependent variables, and now when we do prediction, the variables must be dependent. And if they are not independent, if they are completely independent, it means in our case of data science and predictive model, X is not a feature that will allow to predict Y. And if there is some kind of dependencies, there is some entropy, in this case, we can consider X as a feature. And now we're going to say, okay, at which level that we are going to consider X as a feature? If there is a little bit of dependencies, maybe it's not relevant. And this will depend from your data set about and the feature reduction problem. Okay, so we need to reduce the features so that we consider those that will bring more information that will impact the outcome of the predictive models. Does it make sense? Okay. So as application of the entropy, it is also used to estimate the entropy rate in stochastic processes. And stochastic processes is when you have a sequence of random values or random processes. It's utilized in examining sequences or stochastic processes to ascertain their information characteristics. So I think all of you have heard about Markov chain, right? Okay, Markov chain is basically you have states and you have transition from one state to another. Okay, and we will assume that you have only two states just in a moment. So if I have a sequence of random values, I can calculate or I can estimate the entropy rate by calculating the entropy of all these random variables when n tends to infinity. And these denote the average entropy per symbol as the sequence length approaches to infinity. So this is essential for deducing the predictability of a process, indicating how much history influences the future behavior. This is used in time series. Usually in time series, we're going to have a past that will let us infer about the future. And if this past doesn't carry enough entropy, it means that it will not provide me a good estimation of the future. Okay, so this provides insight into the memory depth of the process. Okay, if I'm going to take a past, what should be the length of the past? Should it be, for example, only 1 day, 2 days, 1 month, 1 year? Because if you increase the past, you have more knowledge, but it's going to be also very heavy in terms of computation. So there is a balance that we need to do between long history and short history to be able to have a good prediction of the future outcomes. So we're going to apply this on the concept of Markov chain. So as already mentioned, Markov chain represent a sequence of random states with transition probabilities depending on the current state. So you can think, let me give you a simple Markov chain example. You can think about Markov chain, a transition between two states, cold and hot. And we're going to have a probability of transition between a cold weather the next day, okay, from cold to hot, and from hot to cold, and also cold to cold, and hot to hot. That's a simple example of Markov chain. We have two states, and we have 4 transitions. 4 possible. It can be 1 transition, 2 transitions, 4 transitions, depending on the model that we have. And for every Markov chain, we try to find the stationary distribution. What does it mean? What will be the long-term state probabilities, transition probability, what will be in average in the long run? And basically, they satisfy the equation as pi multiplied by p equal to pi. And this is the probability that we would like to find. And the sum of pi I is equal to 1. And when we find the information or the transition probabilities, we can calculate the entropy, the transition entropy, as equal to the usual values of the sum of Pig multiplied by the log 2 of Pig, where I and G are the 2 states. So we calculate the transition between the 2 states. Let's illustrate this on a simple example. Consider that you have 2 states, A and B. And we have 4 transitions. The transition between A and A is equal to 0,9. The transition between A and B is equal to 0,1, so they complement each other. The sum is equal to 1, and this is why we said the sum of pi I is equal to 1. Okay? So this is pi of A. This is 0,9, okay, and 0,1. The sum will be equal to 1. Now, B to A is equal to 0,5 and B to B is equal to 0,5. Now, before going into detail, what transition has the highest entropy? A or B?
A.
From A or from B?
From A to A.
Yes.
To B.
No.
From A to B.
From B. Okay, so the transition from B has the higher, because I have higher uncertainty. Now, this is just the common sense. And let's illustrate this through the example. Now, the first thing, we need to calculate the stationary probabilities. Okay, and we've defined this as finding the equation pi p equal to pi. So let's illustrate this. Okay, we solve this equation. We will find pi a. It means the probability of transition from A is equal to 0.833. And the transition from B is equal to 0.167. So you can see here, I have higher probability from A. And here I have smaller probability for transition from B. So as you already mentioned, the uncertainty going from B is higher than the uncertainty going from A. And now calculating the entropy here, that will confirm what we've talked about. Now I have the values of Pig, which is this value. Okay, so I'm going just to apply the entropy equation to these values pi A and pi B, which is Pig, to move from A to any other state. It's the probability to move from A to any other state. You can understand it like this. So we're going to have the entropy of A is equal to 0.469, which is this value, small. And the entropy of B is equal to 0.1 because it's completely uncertain, 0.5 and 0.5. Okay, and the entropy rate we're going to multiply these values, the sum of these values by these values, and this is going to give the entropy rate. It's an average indicating the chain average new information rate. Okay, and this gives 555 bits. This gives us the entropy of the whole transitions in the Markov chain. It's the average of all different type of transitions, basically. Okay, the average entropy of all transitions. Does this make sense? Okay, so the entropy is applied in several areas in data science, as already mentioned. Okay, it can be used to detect the anomalies that can cause significant changes in the entropy of the data set. Okay, like for example, detecting anomalies or introducing disorder and increase of entropy. It's used also in data analysis, and the usage is in the assessment of the complexity and predictability of the data sets. It's used also in cryptographic systems, in random number generations, and entropy sources. So let's finish this class with giving some examples of using entropy in data science. We have already talked about the entropy that will come from a uniform distribution on the bias distribution, and this is just a summary of the mathematical expression. And the relevance in data science we already talked about. It's used in information theory, in machine learning, and also model evaluation. And basically we're going to have to use entropy when we talk about later feature selection, clustering evaluation, and also this is in communication. So that's the Python code that will illustrate the difference between the entropy in uniform distribution, completely random, and bias distribution with less randomness. So basically here in this code, we calculate the entropy manually using this equation. Okay, so we calculate the value count, and here we calculate the probability from a data set. So imagine that you have a data set of random values, which is uniformly distributed, and here we have a distribution that is biased with p equals 0.9 and 0.1. Here it's 0.5, 0.5, it's uniform, and here we have a biased distribution. So for every data set in the uniform data set and in the biased data set, we are going to calculate the entropy manually using these values. So we calculate the probabilities of every data point, and then we calculate the entropy using minus np.sum, the probabilities multiplied by the log 2 of these probabilities. And we use here vectorization and broadcasting. This is here we use vectorization to calculate the entropy over all the values. And finally, this is just a visualization of the entropy of the uniform distribution, which is equal to 1, which is normal, and the entropy of the bias distribution, which is less than 1, because here we have a bias distribution. So we have less uncertainty because most of the outcome will be equal to 0. That's another representation of the same problem. Okay. So the last topic will be the introduction of the cross entropy in machine learning. So you remember, we have talked about cross entropy in one of the lectures in binary classification. So in binary classification, what do we have? We would like to classify an outcome either to be 0 or 1. And usually, we're going to estimate this as a probability. And if the probability, for example, is greater than 0.5, we're going to say this belongs to the class 0 or class 1. And if it is below than 0.5, so we're going to map it to the class 0. Okay. Now, the definition of cross entropy, we're going to use and this is why we use the entropy formula, is equal to the sum of the probability, okay, of the ground truth and the log of the prediction. So the ground truth will be a probability between 0 and 1, and the prediction will be also a probability between 0 and 1. So what does this measure? So if the probability of the ground truth is completely different from the probability of the prediction, what you will have? What will be the cross entropy value? High or small? Yeah, if the value of the if the ground truth probability is very different from the predicted probability, we will have high entropy because you have a lot of variation. Okay? And what we want to minimize in the case of cross entropy classification problems, binary classification problems, we want to minimize the entropy or the cross entropy. Why we call it cross? Because it will measure the uncertainty, the unpredictability between the ground truth and the prediction. Does it make sense? Okay. And this is why we use the cross entropy in machine learning. This is the function that we would like to minimize. So for example, if you have binary classification context, you have the true label is y equal to 1, and your prediction model, it gives you 0.9. So to calculate the cross entropy value, you will do minus the sum of 1. This is the prediction. This is the ground truth probability, which is 1 plus 1, log of 0.9 plus, this is equal to 1 minus y, 0, 1 minus 1, multiplied by the log of 0.1. So finally, we're going to have only this entity here, because this measures the loss that we will have, log 0.9. So log of 1 equal to what? 0. And log 0.9, it's small error. And because why it's small error? Because the prediction is very close to 1. Now, if there is a discrepancy too much, this log is going to have larger values. Okay. So this is the cross entropy equation, which measures the discrepancies between the predicted and the ground truth. Okay, and lower cross entropy, it indicates prediction are close to the true labels, and higher cross entropy, it signals prediction far from the true labels. And look at this illustration now. We've made two scenarios. One scenario where we have a vector of ground truth and vector of predictions, and they are very close to each other. Okay, so this is the distribution of class 0, predicted class 0. Look, it's distributed between 0 and 0.4 or 5, and here this is the distribution of predicted values. So look at the discrepancy here. Look at the entropy. The entropy is very small. Okay, it means that the prediction is close to the ground truth. And here we have completely unpredictable, okay, they are not close to the predictive. So here we have the scenario where the prediction diverges from the true labels. And in this case, we have higher entropy because of that divergence. So this is how cross entropy is utilized for quantifying the error or the loss in binary classification problems. Okay, so we stop here, and there are other applications that we are going to talk about. This, for example, Kullback-Leibler divergence. It's used to measure the difference between two probability distributions, and also the assessment of the complexity of a predictive model. We will talk about this in the next lecture, inshallah.